parentheses for the individual masses of these two merging neutron stars. It is not a neutron star black hole system, which would be inconsistent with these waveforms, but not consistent with the masses of black holes in binary systems. So this is pretty convincing it was a neutron star merger. Because the third antenna was not looking in the right direction, the determination of the location from just gravitational waves on the plane, on the sphere of the sky, was not very good. But there are, well, here is some things that they cite about the theory of mergers of black holes or neutron stars, or black holes and neutron stars. And most of the theoretical useful work is due to Thibaut d'Amour and collaborators. It is very beautiful analysis in powers of V over C of the orbiting objects. And however, the actual analysis requires very complicated numerical general relativity, of which I will not say anything since you had a talk by Kip Thorne recently on this subject here. And for neutron stars, of course, the input is more complicated because neutron stars have an equation of state, which is not well understood, and so on and so forth. Now, soon after the gravitational waves, a couple of satellites, 1 seconds after the merger, saw a signal in gamma rays, and later various people saw an afterglow, which is something that comes after a gamma ray burst and has much longer duration and much lower frequencies than those of gamma rays. And by looking at the afterglow, you can very well locate where the object was that emitted the burst. And it's 140 million light years away. It is corresponding to a redshift of about 1%, which is the smallest redshift of an observed gamma ray burst ever. And it occurs on a galaxy that you see face on and the outskirts of a galaxy close to you. Now, the corresponding paper now on the electromagnetic signal as opposed to the gravitational wave signal, the first paper is this one. And its abstract says, the merger of two neutron stars is predicted to give rise to three major detectable phenomena: a short burst of gamma rays, a gravitational wave signal, and a transient optical near-infrared source powered by the synthesis of large amounts of very heavy elements via rapid neutron capture, something called the R process. Such transits, called macronovae or kilonovae, are believed to be the centers of production of rare elements such as gold and platinum. Now, the key words here are spectroscopic and gold and believed. Now, immediately after they saw the signal, the observers went to televisions and newspapers and so on to announce that huge amounts of gold, platinum, uranium, and other heavy elements were created in the collision of these compact stellar remnants and were pumped out into the universe, unlocking the mystery of how gold on wedding rings and jewelry is originally formed. Someone else said there is about 10 times the Earth's mass in gold and platinum alone. Yet another one of these guys says the collision produced as much gold as the mass of the Earth. That's a factor of 10 different from the previous one, but that doesn't matter much. Mass of the Earth is 10 to the 49 atoms of gold. Now, this is the data on which they base the claims that I just showed you. This is the afterglow's infrared spectrum in 4 times days after the gamma ray burst. And that's the logarithm luminosity, and the horizontal is the wavelength. Now, it says that kilonova model compared to the spectra, the first 4 epochs of kilonova models: dynamical ejecta, wind region with proton faction, so on, and we enrich them with another proton function in green. The curve represents the sum of the three model components. So they have a model of a jet that has three components that they sum with arbitrary coefficients to obtain the black curve, I think it is, and no, to obtain the red curve. The black curve is the observations. Even with all these three combined models, the observations and the signal do not agree. But more important is the fact that if you claim you have seen an element in light from the sky, you have to show features of its spectrum. For instance, helium was discovered on the surface of the Earth. But you may have noticed that there are no lines at all in their spectra, not even of lanthanides or helium or anything. So the claim that they had seen an Earth mass in gold is fake news. They do not have evidence to show that. Now, this is in extreme contrast to the very high quality of the analysis of the gamma ray burst, of the gravitational waves. Now, neutron star mergers like this one produce short and hard gamma ray bursts. Most gamma ray bursts are long gamma ray bursts. What is the difference? Now, this is a very old transparency showing duration in the horizontal scale of a burst versus the number of bursts observed with that duration. And the long ones are above a couple of seconds, and they are simply called gamma ray bursts, so long gamma ray bursts, and the short bursts are below that blue line, and most of them are harder than the ones on the right. So there are two populations. One of the populations is due to core collapse supernovae of type 1c as the mother of these things, and the other one is due to neutron star mergers. Now let me tell you that there is a standard model of gamma ray bursts. It's not one model, it's an evolutionary point of view. And that is called the fireball model. And then there is another model, which is called the cannonball model, and it's the overwhelmed minorities view. And in that one, you don't have fireballs, you have something called cannonballs, as we shall see. Now, this is the standard model of gamma ray bursts, and an object which is not necessarily specified emits shells of E plus E minus gamma plasma that collide with each other as they move out to produce a gamma ray burst. And when the entire object collides with the interstellar medium, which is, has infinite mass effectively, it's like a beam dump, that is what produces the afterglow. In the two cases, via synchrotron radiation from a plasma of turbulent E plus E minus gamma stuff. Of course, they would produce, if it is a turbulent object, unpolarized synchrotron radiation. And that's the same mechanism for the afterglow. Now, this model has a small problem, which is the following. If you worked in a high-energy physics lab, as I did, you wouldn't construct a collider that has the bunches of particles moving in the same direction, because that's not effective in making new stuff. While the beam dump, where all the energy is dumped, is much more effective in producing new things. Now, if you use the parameters that these people use to establish the amount of energy emitted in the gamma ray burst and the afterglow, you get to the conclusion that at least 10 times more energy is emitted in the afterglow. The observation is the other way around. So this disagrees with energy conservation by a factor of 100, which is interesting as the first step of a theory. Now, in spite of that, even a couple of years ago, there were still people writing about energy conserving or not energy conserving models of gamma ray burst afterglows. It's quite a freedom to be able to write papers and have them published in which energy is not conserved and is admittedly not conserved. This is one of the many peculiarities of a community of about 100 or a few hundred people that work on this subject. Now, this is again the standard fireball model. In it, the progenitor used to be what they call failed supernova. Then it became something different called hypernova, and then they became something different called macronova. All of these objects have in common the property of not existing. The geometry of this emission used to be spherical. Then they decided it should be in a funnel. Then they went for a very narrow cone, always observed at an angle 0 to the observer. Of course, that has phase space 0, so probability is 0 to see a gamma ray burst at this angle. The radiation used to be super synchrotron radiation for shocks made of E plus E minus plasma. Then they decided that didn't work, so they added some load of baryons to it, and then eventually it became ordinary matter. All this with the model being always called the standard model. Now let me break here this show for some commercials. The true talk will start in about 5 transparencies. Now this is a picture of a quasar called Pictorius A. And this object, which is on the left, somehow splits stuff that travels for quite some distance, that is to say the size of various galaxies, till it eventually stops and blows up. That's something that happens, and it is due to accretion of matter into a super heavy black hole, and when it accretes by a technique, by its method that is not understood, the black hole sends stuff in one direction and the other. You see here only one direction because it's pointing closer to you, and thus the luminosity, for instance, is higher. Now, this is supposed to be due to turbulent, catastrophic, general relativistic magnetohydrodynamics, which it goes without saying is something that is not fully understood. But it happens in these accretion things. There are tiny imitations of quasars in our own galaxy. They are called microquasars. And one of them is this guy here, which has the following interesting properties. It is a black hole of about 10 solar masses, and it is accreting from a disk that is fed by a companion star. And every month or so, with not quite a periodicity, the disk becomes unstable, the signal of X-rays from the disk disappears, and 2 blobs are emitted in the opposite directions by this not understood mechanism of something rotating very fast, falling into a black hole, and giving rise to 2 balls of matter in opposite direction. And you see here some data on this guy, where you see one of the blobs moving with time towards the left, the other one you don't see, but then it hits a region of higher density, and then you see it higher interstellar density, and then it flames up. There's a flare. And here you see the motion of these things in angular separation to the center of one of the guys in one direction and one of the guys, the other guy, in the opposite direction. These things I will call cannonballs, and they are made of ordinary matter. That's the end of commercials. Now, the cannonball model is due to Arnondar and collaborators. Collaborators is not very many. It's systematically Shlomo Dado, and occasionally myself. Now, let's move towards gamma ray burst. Suppose you have this object, I turn it around, and I superimpose it on the remnant of a supernova that is exploding and has just exploded. Now, supernovae, before they die, emit large amounts of shells of matter that produce a distribution of semi-transparent stuff around them. Now, if you send a couple of cannonballs, because the supernova makes them in opposite directions, this will hit the light of this glory, which is continuously illuminated by the supernova itself, and Compton upscatter the light to higher energies. And that is called glory. And in a gamma ray burst, in a collapse of a type 1c supernova, emitting cannibals of the ordinary matter plasma, when they collide with the light, their electrons collide with the light in the glory, they inverse Compton scatter it to higher energy. So that one cannonball would be a narrow GRB pulse of gamma rays. Each cannonball is one pulse of a gamma ray. Now, this is very simple. You have a large Lorentz factor of an object containing electrons. It's made of matter, ionized, and it hits a roughly spherical distribution of light, and it takes its photons of low energy and kicks them up by what is called inverse Compton scattering to higher energy, and you view that from a certain angle theta. And it's a very forward photon beam of precisely calculable properties. This is the way high energy gamma rays are made in accelerators, for instance. And first of all, you have the shape of the pulse, and that is determined by the distribution in energy of the glory slide, which is measured to be a thin thermal Bremsstrahlung spectrum, looking like this with alpha roughly 1. And then the density of the light decreases with distance from the supernova, like 1 over r squared. With these ingredients, you can work out what the number of photons will be as a function of energy and time in a very simple and precise fashion. And I'm not going to go into the details, but I am showing here a 2-parameter fit to the best measured single pass gamma ray burst. It's a very good fit. Now, this is time, and this is number of counts. Now, in the case of a neutron-star merger, the theory is slightly different, because what matters in neutron-star fusion, which will also emit cannonballs, is the same mechanism of inverse Compton scattering, but on the light emitted by the rotating magnetic field of a pulsar of pulsars. And that also works for the only case, which is the interesting one discussed today, in which we have measured both a gravitational wave and an electromagnetic signal. The gamma rays are fit by the same formula. It's also single pulse one with this expression. Now, one of the first 13 decisive tests of the standard model versus the cannonball model is the polarization. The polarization in all cases of the gamma rays, when it has been observed, is compatible with being very large instead of 0, which is the prediction for synchrotron radiation in the standard model. There are 13 such very simple tests, all of which the standard model fails. Now, one very simple thing. When did we start? 25 minutes ago. Are the correlations of various observables of the gamma ray signal, which you can work out as if the cannonballs, the gamma ray bursts were all identical, except for the Lorentz factor that the cannonballs are moving with and the viewing angle. And this is only simply relativistic kinematics. If you call the Doppler factor, as I wrote in here, it depends on velocity and Lorentz factor. And for large gamma and small theta, which is the realistic case, this is simply the formula of the Doppler factor by which the energy is increased by the motion of the object towards you. For instance, there's something called the peak energy, where the gamma ray burst energy pulse has a maximum energy, and that is proportional to the average energy of the upscattered light times gamma and delta, and with the usual cosmological factor. And the isotropic energy, which is the energy the object would have if you assumed that it was due to an emission which is spherically symmetric, is proportional to gamma delta cube. Now, gamma delta cube is about 10 to the 12th the observed collision energy. So 12 orders of magnitude is the exaggeration used by people when at the beginning of this story they said that gamma ray bursts were the strongest explosions since the Big Bang. They made, in making that statement, two errors. First, the Big Bang was not an explosion in any conventional sense, and then 12 orders of magnitude because of beaming. Now, for the most probable angle, which is of the order 1 over gamma, these things imply that EP is proportional to a square root of the isotropic energy. And this is the correlation observed in gamma ray burst and going over very many orders of magnitude in isotropic energy and peak energy. And you see that it is not a straight line as it would be in an accelerator experiment, because the gamma ray bursts are not all identical, but it is very well satisfied. This is of course not predicted by the standard theory, and so they give it a name. It's called the Amatic correlation. It's a prediction by us, but it's called the Amatic correlation. Now, at much larger angles, the correlation, you can again work it out from the simple formulas I wrote, is EP goes as the cubic root. And I always make this error. Sorry, apologies. So in here we have the short gamma ray bursts, and the ones that are far off axis follow this line, and as predicted here, and the ones that are close to the axis follow this line, and that's the one I'm talking about, the one which was seen also in gravitational waves. And a very simple correlation is between the time the duration of a burst has, say half width at half maximum, and the peak energy of the gamma rays. It's just one is the inverse of the other, and it also works extremely well, and including the guy we're talking about today. So none of this is predicted by the standard model or understood in the standard model. That was mainly stuff about the long duration gamma ray burst and short hard bursts. How about the afterglows, which is what remains shining at lower frequencies than gamma rays for a long time? Now, the afterglow is also something that we understand. It is due to the cannonball moving in the interstellar medium and emitting light from its inner magnetic field by synchrotron radiation. And this is all based in analogies with the magnetic field of a galaxy and so on, but it's fairly simple physics. Now, not going to try to derive this. The most interesting example in which we use the simple formula for the dependence on time and frequency of the afterglow's fluence is this guy in here, a two-peak, that is to say two cannonball moving towards your gamma ray burst, and that's its gamma rays, and in the R band, that is to say a parenthesis around red light, it was observed the afterglow of this thing to move along this data here. And on day 6, when these data were published, we fit the afterglow with this expression and with two cannonballs, because it has two cannonballs, one and the other. And however, we were of the opinion, contrary to everybody else, that these objects were made by the explosions of supernovae. So we plotted also on top of this the red light curve that the supernova should have. And we predicted that on day, on cannonball, the other cannonball, and the supernova, we predicted that on day 10 the supernova will begin to be discovered. Lo and behold, in day 10 the supernova was discovered. And the flux as a function of frequency of a supernova being very different from that of a cannibal, it's very, very clear that that was the supernova that gave rise to this particular gamma ray burst many years ago, as you see, in 2003. Now, before this observation, the progenitor of long gamma ray bursts, according to the standard theory, was either a phase supernova or a hypernova or a macronova. After this discovery, everybody always knew that it was a core collapse supernova. But, of course, now we understand what the progenitor is. It's a supernova. Before we understood what the mechanism was of the gamma ray burst in the gamma rays, which was inverse Compton scattering. So that had to do with the afterglows of long gamma ray bursts. How about the afterglows of short gamma ray bursts? These are, in our cannibal theory, due to the following fact. A pulsar, or two pulsars, lose energy by magnetic dipole radiation. And they are surrounded by an amount of stuff that has been expelled earlier, and it's called a pulsar wind nebula. And if a constant fraction of the energy emitted by the rotating magnetic field of the pulsar is observed and re-emitted by the nebula, then you have an extremely simple formula for the luminosity of this object right after the neutron star merger, which is that its luminosity, normalized to its value at 0, depends on only one parameter, which is the logarithmic slowdown in time of the pulsar's period. And here are all the observed pulsating pulsars, their afterglow up to 100 days or so in X-rays. There are this many being observed. This is the luminosity, and this is the time in TB units. TB is fit for each one of them, and it works beautifully for all of them, including the interesting one today, for which the early afterglow is this one here. This is a two-parameter fit, one for the size and another one for the TB. And it works very nicely also. So we understand the early afterglow of this guy. That was the bolometric afterglow. If you look at the X-ray afterglow, which you can measure to much, much later time, then here I'm showing, and I'll be fast, the prediction of the cannibal model as a function of time for the X-ray afterglow, now up to 200 and some days. And what I said up to now was relatively simple. I don't know what I'm going to say now because I don't remember, but it says it's not so simple. Yes, what is not so simple is the standard model of a neutron star merger afterglow. The standard model, they don't have a standard model, they have 5 or 6 possibilities. They study them out by comparing them with data, and then they choose one possibility with various components for what is emitting the light, and they say that this particularly interesting gravitational wave has a successful jet, which is yellow, that drives a cocoon, which is red, through the interaction with an ejecta, which is blue. Well, this is how they fit the data of various frequencies as a function of time for the flux in millianskis at various frequencies of the light. And since they have 20 parameters or so in this complicated theory, of course they fit it very well. But then the data is prolonged to later times, and none of the predictions work, not even vaguely. And since they have so many parameters, they can, of course, explain it again.
What does FB mean?
FB?
The FB model.
Fireball. The standard model is called the fireball model. I apologize. Well, I said it, but of course, I've said too many things. Now, these things on your left all have the same shape, different intensity, because the frequency dependence is only the power of frequency. So by correcting for the power of frequency, you can put all the data into roughly a single line, which is this one. This is the previous data corrected this way. And this is the time when new data began to happen. Now, the dotted line, the dashed line, is the prediction of the cannonball model when the cannonball is traveling in a roughly constant interstellar medium density, as it does when it's just out of a supernova. When this particular object was coming towards us and exited the region of constant density and entered the region of a density assumed to be 1 over r squared, then there is a prediction. This would be our postdiction of the behavior. So this is a 1 parameter change from r to the 0 to r to the minus 2, and with it we explain everything beautifully. They also explain everything beautifully, but with 15 parameter changes. And this is particularly sensible because this object, this change in density, this object was seen as coming towards us from the outskirts of a galaxy that we see flat relative to us. Now, to finish, I'm going to blow the real cannonball, which is the apparent superluminal motion of cannonballs in the sky. Not of cannonballs in general. This was some possibility first considered by Courdeck in 1939. And the point is the following. You have an object that is emitting light, but it also has emitted something at a highly relativistic speed, which is moving towards you at a certain angle theta. Now, since the light emitted by this object is catching up, so to speak, because of this large beta with the light emitted by this object, the time difference of what you see in here and what you see in here in a particular time of the observation is very short. It is shortened by the fact that this guy is catching up with the signal. So the apparent velocity, which is the velocity orthogonal to you in the sky, may be bigger than the speed of light. And that is the expression here. It's very simple. For the apparent velocity as a function of redshift, beta factor, and angle at which you observe it, which is also rewritten here in simpler fashion. Now, the apparent velocity can be much larger than the speed of light. For instance, for a Lorentz factor of 20, if you see an object at an angle which is 1 over 20 radians, then the apparent velocity in the sky is 20 times the velocity of light. Now, this is such a simple exercise that I advise you very much to give it to your students, because the result is very surprising and the input is very simple. Now, let me rewrite this formula of the apparent velocity with v over c equal to 1, roughly 1. It's a very good approximation in the case I'm going to consider. And this is the theory of an apparent velocity. And this is how you would observe an apparent velocity with that. Well, I'm going to tell you what these things are. The redshift is close to 0. The angular distance to this object in the sky is 39 megaparsecs, and the angle by which it was measured to move in an interval of 155 days is 2.7 milliarc seconds. This is a picture of the observations. This is a 3 sigma region for the object at a certain time in day 75, and then it moved in the sky. Day 230, it was here. Needless to say, this is a cannonball. And these are the observations. And the external lines here are 12 sigma contours around where the position of the object is moving in these two measurements, 155 days one together. So if you input this measured number from here into this formula, you can extract by using this superluminal theory that the angle was 28 degrees relative to you by which this thing was coming. And it turns out, interestingly, that just by looking at the gravitational waves, you can deduce the angle between the observation and the angular momentum of the binary system. And that angle, only from gravitational waves, is 28 degrees. And if you assume that the cannonball was emitted about the angular momentum, then this is a prediction for the angle. So it's a measurement of the angle. If I put this measurement of the angle in here, I get an apparent velocity of 4 times c. So even how much this object moved in the sky is predicted by the cannonball model. So what is jetted in this origin of gamma ray bursts and short gamma ray bursts? Cannonballs. Now I have reached transparency number 0. But since I expected an audience of 100 mathematicians, I did not assume that they would think that I would limit myself to non-positive integers, positive integers. So I'm now going to transparency number -1. And there are very few left. What I told you right now about the motion of a cannonball in the sky is has to do with long gamma ray bursts. And are they also made by superluminally moving cannonballs? The answer is yes. Back to this guy, which allows us to prove our hypothesis that supernovae were the origin of gamma ray bursts. We made a prediction which was for the angular separation between the two cannonballs as a function of time. That was not quite right because we did not take into account this going up and down in here, which is blown up in here, which means that the cannonballs are crossing regions of density of the interstellar medium, which is changing. And once we made this prediction, then our prediction for the distance between the two cannonballs seen in the sky would be this one as a function of time, and this is a measurement in day 57 by Taylor et al. Now the important thing is not the error bars or anything like that. The important thing is that in the standard model you expect the supernova remnant to be the only origin of the afterglow light, and that means if it is unobservable there should be 0 images, unobservable because it's too late, or 1 image if it is still observable. While in the cannonball model there is also the possibility or not that you still see after 50-something days the supernova remnant, but you have to see 2 images of the cannonball. So the prediction is that you should see greater than 2 images, while in here 0 or 1 image. The observation was 2 images, which clearly distinguishes between these 2 possibilities. Now, what did they do with this horrible discovery that they made? Because they discovered that cannonballs were right. They wrote, much less easy to explain is the single observation 52 days after the burst of an additional radio component 0.28 milliards northeast of the main afterglow. This component requires a high average velocity of 19 c and cannot be readily explained by any of the standard models. They agree there's more than one standard model. And the evidence for this, having 2 objects in the sky, is 20 sigma. Now, how did they react to the obvious conclusion that their theory was wrong? Well, they talked about the cannonball model first time ever in the New York Times. And first time ever anywhere, but it happened to be in the New York Times. Now, you would think that, particularly for an observer who earns his or her life by observing the sky, seeing is believing. Well, that happens not to be correct. What these guys wrote in the New York Times is that our observations are sufficient to rule out predictions of the cannonball model. And then a few late daters, they decided to be stronger, and they said a very long baseline imaging of the compact afterglow was used by Frail to unequivocally disprove the cannonball model of the origin of gamma ray bursts. Now this is very interesting socially. It's a social disease, but it is this way. So the conclusion is that one should never trust an observation until it's corroborated by theory. But the real question is whose theory? And In astrophysics, standard theories never die. Only the proponents do. And the three people working on this field are getting pretty old. So soon, the cannonball model of gamma ray burst will be the standard model of gamma ray burst without any quote of its parents. And here's a good place for me to stop.
Any question? Comment? Jim?
Yeah, I've always thought that the afterglow from GW 170817 had nothing to do with the gamma ray burst, but was rather due to the ejected
Yeah, of course.
neutron-rich matter.
No, but you are wrong. It was due to the ejected cannonball, as I proved. It is not due to the jets that these guys imagine, which are the afterglow, according to them, of
Well,
the...
it's nothing to do with the jets either.
There are no jets. There are cannonballs. Their jet model that tries to explain all these things miserably agrees with the data by having 17 parameters. And it cannot, in any conceivable way, describe the motion of the cannonball in the sky. When they show you this picture, what picture? I'm sorry, I'm being thick here. Well, I showed you a picture of something. Here it is. This is a single object observed at 2 different times 155 days ago. It cannot be resolved with the radio precision that they have, so this is an effectively point-like object moving in the sky by this much, and they call it a jet. It doesn't look to me like a jet, it looks to me like a cannonball. Moreover, they don't know the properties of this so-called jet. They call it jet, I think, because it looks to them like a jet airplane seen on a radar screen. You see a point which is moving. You can call it a jet if it is a jet airplane, but otherwise it doesn't look like a jet. This is the afterglow. This is the source of the afterglow of this object.
The afterglow I'm referring to occurs within a week.
That one I have also talked about. The afterglow that you are referring to, I have also explained carefully, and these are the early afterglows, if you wish, of pulsar wind nebulae illuminated by a rotating pulsar. And that is the afterglow in early times, also of 170817, and it's showing here independently of the other. And this is the early time afterglow, and it agrees with what we think it is. It has nothing to do with a jet. It's a pulsar wind nebula illuminated by a rotating star or couple of stars. So this is what they would explain with in a manner of weeks. You see, with these theories, they attempt to explain everything. Well, they are not showing here the first week. For the first week, as far as I know, they don't have very clear explanations. This is the later afterglow, after 1 week or so. Yes, sir.
Well, if anybody asks now himself the question, you have this theory which is not an agreement, just a standard opinion. There are big conferences organized. Have you been at these conferences? Have you given a talk there?
Yes, they used to invite me, and eventually they decided not to invite me anymore.
Were people in the audience?
There were people in the audience who perfectly well understood what I was saying and slowly imitated it in their theories without reference.
That idea you have them still alive in their way?
Say that again?
Well, you said they imitated, so
Yes.
they took over with this idea, but is the idea still alive now, in their way?
Well, let me show you an image from a recent paper by someone of this conviction. Escape. If I can find it. Yeah. You see this? You don't see it. This is our original picture of a cannibal model many, many, many years ago. And this is the standard model in a recent paper. So you see now it's a ball that is moving. It's called a jet, but it's actually a cannonball. It happens to emit light by Compton scattering, which used to be synchrotron radiation for the past 20 years, and so on and so forth. And now the observation angle is no longer 0, as it was always supposed to be. Now there is an angle of observation. Of course, they are getting close to satisfaction. And they've done this again and again and again and again for 20 years. For instance, the change from baryon-loaded E plus E minus gamma plasma to conventional matter, or the fact that the gamma ray bursts of long duration are due to core collapse supernova, all these things they have adopted as if it was their idea, with no citation, except that the ones that I told you about in the New York Times and so on.
So that are wrong.
Yeah. It's a very careful community. They are very well. It's a feudal castle.
100 people?
It's an order of magnitude of 100 people, yeah, 200. But you see, they have various peculiarities that explain what's going on. One of them is that all papers are co-signed by theorists. And the interpretation of the observation is not that that the data suggests, but what the theorists want. These same theories are the ones that give observation time to satellites and so on. So from the time when they disprove the cannonball model by seeing 2 cannonballs, the fact that they said that the cannonball model was completely destroyed meant that nobody that has suggested to look with radio antennas to the late afterglow of a gamma ray burst ever had the proposal accepted, because it would see the cannonballs. It's very efficient. It's like a church. That's the only interesting part of this story, that these things happen in science. It's quite inconceivable.
I have a very vague question. I probably didn't understand what you're saying, but so in these 2 different models, polarization of the radiation will be different, right?
In one of them it's 0, and the other one is order 1. Yes. In Compton scattering, you produce, unless you are precisely on axis, a radiation which is polarized in the plane of where the object was going and where you see its Compton scattered light. And the prediction for synchrotron radiation from a turbulent plasma is, of course, 0. And the prediction for Compton scattering is non-zero. It depends on the angle at which you observe it. Here you have it. So this is the polarization for a given Lorentz factor of 10 to the 3 as a function of the angle, and it peaks at 1 over the Lorentz factor. The amount of polarization peaks at 1. And in the region where the flux is maximal, which is around here, the polarization is compatible with being a very large number. And if we look at the numbers of the 13 cases or so where the polarization has been observed, it's always compatible with being from here to here and never compatible with 0. So there's a very simple, very, very simple distinction.
Thank you very much.
You're welcome.